Okay, get you to recall with me, when I want to calculate, like say I wanted to figure from A to B, the area under the curve, call it A. A couple of ways we did that. We started out with approximate. That area from A to B approximately was equal to, remember we divided it up into rectangles and took left-hand endpoints, right-hand endpoints, remember all that good stuff. Let's say I did 3 rectangles here, and this was x1, x2, x3, this would be x0. And the way I approximated was, yeah, if I use right-hand endpoints, I said, well, let's come up here, that approximates part of the area, then that would approximate another part, and then that would approximate. So the area was approximately equal to the sum of all those areas of those rectangles, right? It was approximately equal to I equals 1, and I did 3 here, but it could be any, pick any n value you want. Now the area was, the width is what we call delta x, and then the height was the function value. In this case, it was the right-hand point, so it was the function value at x1. But we said, that could be any sample point, if you will, in that interval. Could be right-hand endpoints, could be left-hand endpoints, could be midpoints, and so that would be the height, depending on where you took the sample point, times the width, which is delta x. Remember all that? Sort of vaguely recall that. Okay. So that was an approximate. Now to get the exact value of that area, we said do more rectangles. Matter of fact, run the number of rectangles to infinity. In other words, make n be infinity, or take the limit as n goes to infinity of that. And that turned out to be a nice, lovely little thing we called what? That was the integral, right? Turned out that was the integral, a to b, f of x dx. Right? You remember that, right? Maybe a little bit? Okay. And it turned out the integral was nice in that it turned out that was the antiderivative. You can figure out the antiderivative of your function. Now sometimes that's harder than others, but anyway, that's what it came. This integral represents this area under the curve from A to B, right? That's what the integral was geometrically interpreted anyway. Okay, well, so now that was for, I didn't write it up here, but that was for a single variable function, one variable function. What happens when we have a 2 variable function? Well, of course, as we know, when we have a 2 variable function, that means we're going into three dimensions here. And we've got a function, wherever it is, let's just make it up here and make it kind of easy on ourselves. I'm going to make, okay, so we've got this, I'm not even going to draw it yet, just to talk about it first. I've got this shape, whatever it is, this z, gives me the height or whatever, but I've got this shape, whatever the shape is. Okay, well, it turns out what we're going to do is we can figure out the volume from the shape, wherever it is, to the XY plane. I can figure out this volume, and that's what we're going to talk about here. So instead of talking about area now, since we're dealing in 3 dimensions, we're going to talk about volumes. So what we can do is we can take, all right, and so over here we did rectangles, and you know, it was based off of how much delta x, the width there was, and how many rectangles we had. Well, when we go to this 3 dimensions, what we're going to do is we're going to take this rectangular area in the xy plane, and let's just say we do a first quadrant rectangular area, and that's going to be, call it R. Okay, and so we've got this surface out here, 3-dimensional surface. Well, what I can do is let me translate this over here. That would translate in this first quadrant R region that I've decided upon. What I've got then is I've got this surface above. Let me draw kind of the one I've got on my paper. All right, so if I project that up to the surface here, what that's going to involve is this part of the surface for Z here. And I've got and so what I'm going to do is find this volume from the surface above this rectangular area. We're going to start with the rectangular area anyway. And I'm going to find that volume from, this is my curve, so I'm finding that volume from the XY plane up to the surface. That's what I'm going to try to approximate here and calculate eventually exactly. So that's the idea. So instead of area, I'm dealing with volume. So I want to know what is that volume there. Okay? All right, now, so how do I do that? Well, just like I divided up the x-axis here into parts, I've got to divide my rectangular region up into parts. Now, of course, the complication is I've got 2 dimensions I'm dealing with, and so I have to divvy up the x's and the y's into increments, and they don't have to be the same number of increments. Here I could have, what does it matter? I could do, let's do 4 increments for the x, so I've got a change in the x, that'll be my delta x, and then I can divvy up the y's into 3, let's say, so I've got a change in the x and a change in the y, okay? And so if I put those together, yeah, I've got, instead of, instead of just a one-dimensional change in the x, here I've got a change in the x and a change in the y, and we'll just call that little rectangle there, Rij, for a general purpose, because like I said, the x's could be divvied up into different number of intervals than the y's. I mean, they could be the same, but probably not. So you've got a lot of complication, as you know, when you go to 3 dimensions. All right, well, what does that all mean over there on when I'm going to this volume? Well, this little Rij rectangle then would be, it'd be a little rectangle over here. Rij right there. Okay, and so each one of those individual rectangles, I can project that up to the curve, right? So this goes up here, and depending on where I want to take those interval points, It's a little messy there, but wherever I want to take, so I figure out then my height based on, where do I want to take it? Do I want to take it in the corner? Do I want to take it in the midpoint of both? Depends. We don't necessarily have to, change it. On these, we did midpoints and left-hand endpoints, right-hand endpoints. It got pretty complicated with it, but, it's complicated enough. We'll do one with, I think we're going to do lower right corners, do it that way. But you see the complication here. We're talking volumes, and you can do midpoints and right-hand endpoints for X, and I guess you could do a right-hand endpoint for X and a left-hand endpoint for Y, or an upper end. So it gets complicated. All right, but each one of these then, this Rij, what that sets up, it's just a thin rectangular box. It's what you wind up with here. Let's see. Let's put this up here, and then don't really see that one, I guess. My best rendition. Okay, so you get bunches of these little boxes. So this is just one representative. In this case, what I have, if I did them all, I'd have 12 of them. Okay. So if I added up all 12 of those, that's going to give me an approximation of the volume. So let's see if we can figure out each of these boxes. What's the volume of that? What's the volume of that going to be? Well, like I said, this measurement here, what would that be? What would that translate to be? Well, I guess it's that, which is the change in the Y. That'd be the change in the Y. So that'd be my length, my width. Well, that'd be this one, which is the change in the X. And then the height of the box, well, that's where you do your function value. So it'd be the function value at whatever X sub I, Y sub J you're at. Okay? And those could be left-hand endpoints, right-hand endpoints. It doesn't, could be anything of your choosing. All right, well, like I said, the volume is just length times width times height. Now, the one little, so it'd be the function value at the X sub ij star and the Y I sub j star. That's your height. Now what they do for the delta x's is they usually, generally speaking, approximate that or notate that as delta A. Delta A is just the area there of that rectangle, delta x times delta y. We'll talk more about that later on, but anyway, sort of makes sense. The volume of each of those boxes is just like it was over here. The area of these is, your function value times delta x. Well, here you got to do volume, so you got to do delta x times delta y times the function value. Delta x times delta y, we're going to notate it as delta A. So that's each box. So if I add up all those, here's the volume V is going to be approximately then, all right? So I've got to do two summations because I've got I's and J's, X's, for the x's and the y's. So so you got to do the summation on the i's and the j's. And again, they don't have to be the same amounts there, so m and n to denote, I've got different amounts there. Change them, dividing them up into different amounts there. So you've got a double summation there, and so we're doing the summations of all these. So that gives us an approximate. So this right here would be doing all of these boxes here. So if I can, approximate that, or draw those in and approximate those volumes, that's what that represents. It's putting all of those, adding up all of those. Okay. All right. Well, how can I get, so that approximates the volume, because that's just gonna, that squares it off at the top here, just like our rectangles squared it off. All right, so that's the same thing this does. It doesn't get the curve, actually. It just, squares it off. So that's an approximate. Well, how could I get an exact, how do you think I'm gonna get an exactly equal volume? Well, I'm going to run both of these to infinity. I'm going to run n to infinity and m to infinity. So let's just write it this way. Run those both to infinity. What do you infinitely many of these little boxes? That'll make it exactly equal. Just like running this one to infinity made that an exact. All right, well, hopefully then you get the idea. So if this is an integral, one summation running into infinity, that gives me an integral. Well, guess what? Here it gives me a double integral. So that's where the idea of double integral comes from, is now we've got two summations that we've got to run to infinity. And so this is going to be our double integral. And in this case, we're doing the double integral over this rectangular region R, so we'll notate it like that. All right, so this is f of xy that I'm doing the double integral of, and then delta A, that becomes just like delta x over there became dx. Delta A becomes dA, and we'll talk more about that, but that's what a double integral means. It's a summation of a bunch of rectangular boxes. So it's pretty complicated, yeah. And like I said, luckily we won't have to do a whole lot of these. We'll do one where we approximate it, but we're going to mainly focus on how do we do these double integrals. But all right, so yeah, let's do one where we approximate it. But understanding kind of what it is we're finding is helpful. In this case, these double integrals, what are we finding? Well, we're finding a volume under the curve, between the curve and the xy plane. Okay, so let's do this one. Estimate the volume that lies under the region R equals 0.3 by 0.2 that lies under that region, and below z equals 16 minus x squared minus 2y squared. Here's how we're going to do that. We're going to divide r into 6 squares. And use sample points as the lower right corners for each r, I, and j. Okay. A little bit wordy problem, but okay. And I'm not going to, probably I'm not going to try to draw this thing here, but what that looks like. But I am going to draw r here. All right, so what does this mean? R equals 0,3 by 0,2. So what the usual rule of thumb is, the x's are first, the y's are the other. Okay, so this is the values I'm going into x. This is what I'm going into y. So these are the x's, this is the y's. And so r here is just a rectangular region. All right, so I'm going x is 0 to 3, and then y is 0 to 2. I'm just drawing r here. So divide r into 6, so this is r. Divide r into 6 squares, equal size squares, so that would just be, what this would be. The good news is the changes in the x's and the y's are just ones. Right, delta x would be 1. Delta y would be 1. All right, so estimate the volume. So our volume is going to be approximately the all this the double sum there. So in this case, we've got the i's for the x's are running 1 to 3, and then the j's are running 1 to 2. And then so what this means here is, I'm going to, and it says use the sample points as the lower right corners, all right? And so let's just start with the lower right corner of this one. So that would be the point, what, 1, 0? And so the function value I would take for it would be f, so this volume is approximately f of, all right, so 1, 0 is the first sample point, if you will, that I'm going to use. Everybody with me? The lower right corner, so I'm going to use that point. F of 1, 0 times delta A. Well, the good news here, again, like I said, delta x is 1, delta y is 1, so delta A is also 1, because delta A is just delta x times delta y. So that's just 1 times 1, which is 1. So that's good. The delta A's are always 1. I don't know if that's the case in the homework, but in this particular case it is. It's just delta x times delta y, so whatever that turns out to be. All right, then I move on to the second one, which would be this one. All right, so that's 2, 0. So I would do the function value at 2, 0. That's going to give me the height, if you will, of the box. So I don't have that out here, but that's going to give me the height of the box. Times then delta A gives me that length times width, but it's kind of it's just 1. Okay. All right. 3, 0 is the next one. So I do f of 3, 0. That would give me the height, and then times delta A. then I go to the upper squares here, but I'm doing the lower right, so it'd be, what would be the next one? F of 1, 1. Times delta A, which is 1, and then 2, 1, and 3, 1. So F of 2, 1. F of 3, 1. So I'm just adding up all those. So I just I've drawn just the base of it, but these are just volumes of each one of those boxes, approximately. That approximates the volume. Is everybody okay? Good with that? All right, so yeah, so to get this value, we just go back to the original function. This is our f of xy right here. So we're just going to plug in, the x and y is showing there. So I do 1, 0, x is 1, so that'd be what, 16 minus 1, 15. 2, 0, so x is 2, 16 minus 4, that'd be 12. Times 1, which is 12. 3, 0, so it'd be 16 minus 9, minus 0. 7 times 1 is 7. 1, 1, so x is 1, y is 1 for the next one. So it'd be 16 minus 1 minus 2, is that 13? 2, 1, x is 2, so that'd be 16 minus 4 minus 2, 10. And last but not least, 3, 1, so 16 minus 9 minus 2 is 5. Did I do those right? Do I believe that? So the volume is approximately 27, 20, 47, plus 15, 62. Approximately 62. Question?